we're going to give some worked examples of systems of linear equations. Let's do an extended review on some of the concepts we've discussed so far on systems of linear equations. Let's say that we have a system of m equations and n unknowns. We'll write this here as our system, capital S. You'll notice that the goal is we'd like to solve for the variables x1, x2 through x sub n. We can express this as a single equation, a times x equals b, when we invoke the following matrices. Capital A will just consist of the coefficients a, I, j. This here will form an m by n matrix. X is a collection of the variables that we'd like to solve for. This here is an n-dimensional vector consisting of the variables x1, x2 through xn. And finally, b is another collection of scalars. This is just what appears to the right-hand side of the equal sign. This is an m-dimensional vector consisting of the scalars b1, b2 through b sub m. We'd like to make some definitions about this system of linear equations, S. We'll say that a vector lowercase s is a solution if a times lowercase s equals b. The collection of all solutions lowercase s will just be called the solution set of our system. We'll say that our system is consistent if there exists a solution. Otherwise, we'll say that our system is inconsistent. And finally, we'll say that our system is homogeneous if the right-hand side just consists of zeros. That is, if our vector b is just the zero vector as an m-dimensional vector. Otherwise, we'll say that our system is inhomogeneous. There's a theorem that tells us properties of the solutions to our system. Again, say that we have a system, capital S, that's in the form a times x equals b. We'll denote k sub h as the solution set for the homogeneous system a times x equals the zero vector. Then k sub h is just the null space for our matrix A, and in particular it is a subspace whose dimension is n minus the rank of our coefficient matrix A. Let's say for the moment that m is less than n. That is, the number of equations is less than or equal to the number of variables. Then there exists a solution, lowercase s, to the homogeneous system where not all of the coefficients of lowercase s are zero. That is, we can find a solution to the system a times x equals the zero vector where not all of the a1, a2 through a sub n are equal to zero. Next, let's let capital K denote the set of solutions to our system, capital S. Let's assume for the moment that our system, capital S, is consistent, and let's denote lowercase s sub 0 as one solution. Then all solutions are of the form lowercase s equals s0 plus lowercase k for some lowercase k that is a homogeneous solution. That is, we can write capital K as just lowercase s0 plus k sub h, where k sub h is the solution set for the homogeneous system. Finally, let's say that m equals n. That is, the number of equations is exactly equal to the number of unknowns. Then our system, capital S, has exactly one solution, S0, if and only if A is an invertible n by n matrix. Next, we'd like to discuss some methods on how we can actually find these solutions. We'll say that a matrix is in reduced row echelon form if it satisfies the following conditions. First, let's take a look at the rows of our matrix. If a row has non-zero entries, then moving from left to right, we'd like to take a look at the first non-zero entry. If the first non-zero entry that we find is the number 1, we'll call this a pivot, and the variables in our system corresponding to pivots will be called leading variables. We'll see an example of this later on in the lesson today. Now let's take a look at the columns. If a column contains a pivot as above, then all of the other entries in that column must be 0. Third, if a row contains a pivot, then every row above this one has a pivot that appears, but this pivot appears further to the left than the row we're in. Given a matrix A, recall that there are just three types of operations we're allowed to make on the rows. The first is a type 1, that is, we can interchange any two rows. The second is a type 2, that is, we can multiply a row by a non-zero scalar. And the third is type 3, that is, we can add a scalar multiple of one row to another. Putting all of this together, we see that there is a series of steps where we could start with an m by n matrix A and arrive at another m by n matrix B that is in reduced row echelon form. First, let's say that we're dealing with the row and we have a non-zero entry. We'll call this our cursor entry. If every entry in this row is 0, then we have a row of zeros, so we'll simply swap with a row below that is a non-zero row. That is, it has at least one non-zero entry. Swapping rows, of course, is a type 1 operation. Next, once we have this non-zero row and we're at our cursor, let's divide the entire row by this non-zero entry to make this non-zero entry equal to 1. This now says that our row has a pivot. Of course, dividing through by an entry is just a type 2 operation. Third, we'll now add multiples of this row to all of the other rows to make sure that this column only has one non-zero entry. This, of course, is a type 3 operation. Finally, we'll move to the row below and move our cursor over one entry to the right and perform these steps all over again. We'll denote RREF as the reduced row echelon form of A once we perform these steps. This algorithm is known as Gaussian elimination. There are a couple other concepts that we'd like to remind you of today before we do move on to the new topics. Let's say that we have an m by n matrix, capital A. Recall that its transpose is that n by m matrix that we find by simply swapping the rows and the columns. The column space of A is that subspace that's generated by the columns of A. That is, we simply take a look at the span of the columns. You'll see here in red where we've looked at the first column of A, A11, A21 through AM1, and now we'll view that as an m-dimensional vector. The span of these m-dimensional vectors is what we call the column space of A. Similarly, the row space of A is that subspace generated by the rows of A. It's a little bit easier to think of what's happening with a transpose. Here we placed in red the first column of A transpose, A11, A12, AN1, which of course is the same as the first row of A. You'll notice now how we can define the row space of A as simply the collection of linear combinations for the rows of A, equivalently for the columns of A transpose. Here are some key results which are not in the book, but we'll discuss some examples of these today. Let's say that A is an m by n matrix, and let's let B be the reduced row echelon form that we find by looking at Gaussian elimination. Finally, let's let S denote the collection of pivot columns of B. That is, they'll be those columns where we have the pivots of our matrix. First, the row spaces of A and B are the same. Not the column spaces, but the row spaces. Remember that these will be the subspaces spanned by the rows of our matrices. Second, S, the collection of pivot columns of B, forms a basis for the column space of B. Third, we can compute the rank of A as simply the number of non-zero rows of B. Equivalently, this is the number of pivots that we have in our matrix B. Finally, let's say that M equals N. Then A is an invertible matrix if and only if its reduced row echelon form is the n by n identity matrix. As a caveat, this proposition does say that the row spaces of A and its reduced row echelon form are the same, but the column spaces might be different. We'll see some examples of this later in the course. Let's make a few observations here as we start to introduce some new material. We'll begin by considering this example of two equations and two unknowns. Let's say that we have x plus 2y equals b1 and 2x plus 3y equals b2. We'll try to keep track of the coefficients on the left-hand side by using this 2 by 2 matrix A, namely 1, 2, 2, 3. Of course, we'd like to solve for x and y, so we'll do this by essentially using Gaussian elimination. First, we'll try to isolate x. That is, we'd just like to have one equation by itself involving x. To do this, we'll add -2 times the first equation to the second equation. Of course, because this is an elementary row operation, this is the same as multiplying our matrix A on the left by an elementary matrix. Next, we'd really like to isolate y by itself, so we'll do this in a couple of steps. Let's multiply the second equation by -1 so that we can find a pivot. Since this is just an elementary row operation, we can now multiply by an elementary matrix again on the left, but now we find the matrix 1, 2, 0, 1. Notice that we actually have pivots in the first row, first column, and the second row, second column. Finally, to isolate y, we'll add -2 times the second equation to the first equation. Again, this is just an elementary row operation, but now once we perform this, we find the identity matrix 1, 0, 0, 1. Finally, putting all of this together, we see that we've actually computed the reduced row echelon form of our coefficient matrix A. We find that the reduced row echelon form is just the 2 by 2 identity matrix. The previous proposition then asserts that our matrix A must be invertible. Actually, if you stare at the equation at the bottom of the screen, you see that we've actually computed the inverse of A as just the product of elementary matrices. In fact, you'll see here in red that this inverse matrix actually appears as the coefficients for our entries, our scalars, b1 and b2. Actually, once we've done this reduced row echelon form, we see that these entries, -3, 2, 2, and -1, actually do give us the inverse of our matrix A directly. Let's actually try to do this in a much more general sense. Again, let's say that we have a system of m equations and n unknowns, and for the moment, let's say that maybe m equals n, just like in the previous example. It'll be a little bit easier for us to express the coefficients here as what's called an augmented matrix. The scalars on the left-hand side just correspond to our matrix A, but on the right-hand side, if you notice the way that we've placed these scalars, b1, b2 through b sub n, we can really think of that as corresponding to the n by n identity matrix. Now, let's say for the moment, just like in the previous example, that we can perform our Gaussian elimination so that on the left-hand side, we find the identity matrix again. That is, we can maybe solve x1 is some sum of the b1 through bn's, x2 is similar, all the way down through xn is something similar. In this case, what we've actually done is we've computed the reduced row echelon form of our augmented matrix. Now we see that on the left-hand side, we would find the identity matrix, but on the right-hand side, we actually find the inverse of our matrix A. Again, this is just like our previous example. You'll notice here that we actually have a unique solution. That's just, of course, what appears on the right-hand side of the equal sign. So we'll say that our solution is S0 is the inverse of A times B. Notice that our two systems, capital S is above as was given originally, and S prime below, which is what we find after performing the Gaussian elimination, gives us the same set of solutions, namely the set capital K, which just consists of one vector. In a more general sense, let's just start with the matrix A, and let's say on the right-hand side we have our n by n identity matrix, I sub n, and let's perform the reduced row echelon form. In general, we'll find on the left-hand side some matrix B, and on the right-hand side some matrix E. Of course, the whole point of doing this is on the left-hand side, we really want to compute the reduced row echelon form of A. But we've already seen that in doing this, we really are multiplying by a series of elementary matrices on the right. So we find that B equals E times A for some product of elementary matrices, E. We've already seen that the left-hand side, B, is the identity matrix if and only if A is invertible. Of course, recall that the E here is just the inverse of A. But let's say, even in the case where B is not the identity matrix, then we actually know that all solutions must be in the form S0 plus K, where K is in our K sub H, which, if you recall, is just the null space of left multiplication by A. Let's denote P as the nullity of our matrix A. That is n minus the rank. Of course, then if we have a basis for K sub H, then we can actually write every solution S to our system A times X equals B as S0 plus K, where lowercase k is a linear combination in terms of these basis vectors for K sub H. Let's give another example of this to try to hit home what's really happening here. Let's say now that we have a system of two equations and three unknowns, x, y, and z. Doing some algebra, we see that a solution to this system, capital S, is S0 plus a scalar t times u sub 1, where S0 is the vector you see on your screen, and u sub 1 is this vector, -3, 0, 1. Actually, you can check that this vector u sub 1 is in the null space of our coefficient matrix, and you can moreover check that K sub H is actually spanned by this one vector u sub 1, showing that the nullity of our matrix, that is the dimension of K sub H, is just 1. This moreover shows that every solution, lowercase s, to our system is in the form S0 plus K, where K is an element here of K sub H. It's just in the form up above, S0 plus T times U sub 1. Let's continue to work through some examples of all of these concepts. Remember that the goal in all of this is simply to solve a system of linear equations. Let's consider the following system. Here we have three equations and three unknowns, x, y, and z. We're going to express this system now as our augmented matrix you see here on the right. Notice that we have the coefficients on the left, 2, 8, 4, 2, 5, 1, 4, 10, -1. We then place a vertical slash to remind us where the equal signs are, and then we have what's to the right of the equal sign, namely 2, 5, 1. We're going to really think of the augmented matrix as just being shorthand notation for what's actually happening for our system. We're going to work to find a solution to this system, and in fact, we're going to show that this solution is unique, namely that it's 11, -4, and 3. The idea is to perform a series of row operations on the augmented matrix because that'll be a little bit quicker than performing operations on the equations in capital S. Here at the top of the screen, we've just rewritten the system that we'd like to discuss. Our very first step will be to isolate the variable x. That is, we want to eliminate it from the various equations, so we just have x to appear once. We're going to eliminate x from the second and third equations as follows. First, let's take the first equation and divide it by 2. This will make sure that we don't really have any funny coefficients to play around with. You can see here in the middle of your screen that the second and third equations are left alone, but now the first equation becomes x plus 4y plus 2z equals 1. Intuitively, we've made sure that we have a pivot in the first row, first column. Next, we're going to subtract twice the first equation from the second and 4 times the first equation from the third so that we can eliminate the 2x and the 4x from the second and third equations. You can see here that all we've done now is really placed it so the first column is 1, 0, 0. We've achieved our goal. We've isolated x so that it only appears in one equation. At the top of the screen here, we've written the equations we've had from the previous screen. Now we'd like to move on and isolate y. Of course, what we'll do is we'll eliminate y from the first and third equations, and we'll just leave it in the second equation. To this end, let's divide the second equation by -3. This, of course, is to get rid of the funny coefficients, but intuitively, now we have a pivot in the second row, second column. We'll now subtract 4 times the second equation from the first, and then add 6 times the second equation to the third. This is to eliminate the 4y in the first equation and the -6y in the third equation. Now we've isolated y so that it only appears in the second equation and nowhere else. Notice that now in the second column we have a 0, 1, 0. Here at the top of the screen, we've just copied the system that we had from the previous slide. Finally, we just like to isolate z by itself. To do so, of course, we're going to eliminate z from the first and second equations. So as before, let's divide the third equation by -3. This is really the same as determining that we have a pivot in the third row, third column. Next, we'll add twice the third equation to the first, and then subtract this from the third equation from the second, so we can just eliminate and have z by itself. You'll see here that now we really have solved for x, y, and z. You'll also notice that for the augmented matrix, on the left of the vertical slash, we have a 3x3 identity matrix. In other words, now we see that the solution is indeed unique. Thanks very much for watching.